Hi, my camera seems to have messed up a little bit or is not working, so I'm going to have to do this a little bit differently than I normally do it. So what I want to talk to you about today in this lecture is doing optimization problems, or max-min problems. And so this is where we start doing word problems. The first thing you want to do when you are doing a max-min problem is you have to understand the problem. If you don't understand what they're asking, or you can't see it, or you can't draw it, then you're going to have trouble solving it. So you want to make sure you understand what they're asking, what you know, what you need to figure out. The next thing you want to do is try to draw a picture. So you can label it and say, okay, this is what I'm looking for. I know this, I'm looking for this. And then once you have your picture, you want to introduce notation. Like, okay, if you're doing a square, you want to say, okay, this side is X and this side is also X. Or if it's a rectangle, one side's X, one side's Y. And you want to start talking about what you need, what you know in terms of the notation. Because your goal is to write an equation for what you are maximizing in terms of one variable. Once you do that, you take the derivative, set equal to 0, because that's where you have high points and low points, or where the derivative equals 0. So you take the derivative, set equal to 0, and solve. And typically, if I ask you for the maximum of a problem and you only get one answer, the answer you get is the maximum. Or if I ask you for the minimum and you only get one answer, the answer you get will be the minimum. So you don't have to worry about, oh, how do I know if it's a maximum or a minimum? You go through the same process to find a maximum or a minimum. But then you could take it a step further to say, okay, I know for sure this is a maximum because of this, or I know for sure it's a minimum because of that. If you only get one answer, typically it's going to be the one I ask for. If you get two answers, then you have to figure out which one's the max, which one's the min, and we'll see an example of that in later on in the lecture. But after you take the derivative, set equals 0, and solve, you will find the extrema. Okay, so let's do a bunch of examples. First off, let's say you have a dog, and you have 1,200 feet of fencing, and you want to find the maximum area that you can close off for Fifi in a rectangular pen using this 1,200 feet of fencing. So I have my fencing. I wrote the horizontal, labeled as X, my vertical is Y. So now I know that if I've got 1,200 feet of fencing, 2X plus 2Y equals 1,200, and then I will solve for one of my variables. Simplifying, then I get X plus Y equals 600, and Y is therefore 600 minus X. I want to maximize area, and the area of this pen is X times Y, so that's my next equation. Area is X times Y. I get rid of the Y and replace it with this, what I solve for over here, my constraint. Y is 600 minus X. I plug that in, and then I multiply through, because it's much easier to take the derivative of this than that. I don't want to have to do the chain rule. Taking the derivative, I get 600 minus 2x, I set equal to 0, and then I get x equals 300. Plugging that into my y equation, y is 600 minus 300, which means y is 300. At this point I go, okay, what were they asking me again? I need to go back and look at the question. Were they asking me for the dimensions? Yay, I have it. No, they asked me for the maximum area, so I don't have it yet. So the maximum area is x times y. So I have to multiply x times y. The maximum area is now 90,000 square feet. That's a lot. Anyway, 90,000 square feet. Now, next problem. Suppose you realize you have a barn, and the barn can be used for one side of this fencing. So then you only need to use fencing on 3 sides instead of all 4 sides. So now your constraint is 2x plus y equals 1,200. Again, I'm going to solve for y, because y is all by itself and I don't need to divide by 2. I want to solve for y. The area is still x times y. So I plug my y in, multiply through, I get 1,200x minus 2x squared. Take the derivative, set equal to 0, and solve. I get x equals 300 again, but this time y is 600 because I don't have to use that other side, so y cranks out to be 600. So the maximum area now is 180,000. Now, the next example, you got a new dog, and they don't like each other. They don't like each other a lot. So you need to buy strong fencing so they don't hurt each other. The outer fencing is $3 a foot, and they're too stupid to know that they can go off the sides and get to each other. The middle fence has to be much stronger, and it's $6 a foot. What dimensions do we make to make so that it costs the least amount of money? So first thing I want to do is I want to label the sides. So the long side is X, long side is Y, and the vertical is X. The area I determined was 1,000 square feet because that's the best for two mean dogs. And then I'm going to solve for Y. So Y is 1,000 over X. The cost is, well, I have 2X plus 2Y, so the outer fencing is 2X plus 2Y. And I multiply that by 3 because the outer fencing is $3 a foot. This middle section is of length X, just like the edge, the side point here, and that's $6, so that's going to be 6 times X. Simplifying, I get 12X plus 6Y, and then I plug in 1,000 over X for my Y. So my cost equation is 12X plus 6,000 over Y. Now I take the derivative and set equal to 0. I'm going to bring this guy, the 6,000 over X squared, over here, and then I'll cross multiply and divide by 12. So I get 12 equals 6,000. Oh, no, I don't. 12 equals 6,000 over X squared. So X squared is 500. I solve. I get X equals approximately 22.36. Plugging that back in over here to get my Y. My Y is 44.72. What were they asking me? Oh, thank goodness, the dimensions. So all I need to do is come up with the dimensions, and my dimensions are here. So the best dimensions would be 22.36 feet by 44.72 feet. Now, next, okay, so I think we've done all the fence problems. Next question. Suppose we want to make a cylindrical can, and it has to hold 100 liters of oil. I want to find the dimensions that will minimize the cost of the metal to manufacture the can, which means I want to minimize the surface area of the can. So let me draw a picture here. I've got the circle on the top and the bottom. The radius is labeled. The height is labeled. The surface area of a can, I have the top and the bottom. So I have, first I need to deal with my constraint, don't I? My constraint is the volume must hold 1 liter of oil, which in terms of three-dimensional things, I'm not saying that right. I need to write this in terms of length, height, and width. So that's the same as 1,000 cubic centimeters. So, and the volume of a can is pi r squared, which is the area of the bottom, times the height. So the volume of the cylinder is pi r squared h, and that has to equal 1,000. Solving for one of my variables, I'm going to solve for h because I don't want to take a square root. So I get h is equal to 1,000 over pi r squared. Now the surface area of a can, I have the top, which is pi r squared, and the bottom, which is pi r squared. So I have 2 pi r squared for the top and the bottom. I also have the outer edges, which imagine if you were to cut the can vertically and unroll it, then you would have a rectangle whose base is the circumference of the circle, which is 2 pi r, and the height of your rectangle would be h. So the surface area of my can is 2 pi r squared for the top and the bottom, and then 2 pi r h for the sides. Let's see, now we've solved for h. H is 1,000 over pi r squared. I'm going to plug that in for h, and I get a mess. I get 2 pi r squared plus 2 pi r times, that gross, 1,000 over pi r squared. Simplifying, let's see, my pi's cancel, one of my r's cancel. I still have 2 pi r squared from this first chunk, but the second chunk has simplified to 2,000 over r. Now I take the derivative of that. I get 4 pi r minus 2,000 over r squared equal 2,000. I'm going to bring this chunk over, solve for solve for r. I'll get r cubed equals 4,000. I can't talk today. R cubed equals 2,000 over 4 pi, which means r is equal to 5.419. Thank you, calculator. Plug that back into my h, and I get that h is equal to 10.839. So the best dimensions for this oil can, is the radius is 5.419 centimeters, and the height is 10.839 centimeters. Next problem, and the last problem we're going to do today in the slides. are building a box out of cardboard. Suppose you have a 10-inch by 10-inch piece of cardboard. We want to cut squares out of the corners to make an open-topped box. What size should we cut to maximize the volume of the box? So here's a picture of what's happening. Here's my piece of square cardboard. I cut corners, same size, and then these flaps get folded up to form an open-topped box. I'm told that the side of this cardboard is 10, and so I'm going to label that 10, and I'll label this little square X because that's what I'm trying to figure out. What size should we cut? Now the volume of this box, the volume of a box is length times height times width. So think about this. The length from here to here, that's going to be the width of your box. And if from the outer edge to the outer edge, it's 10, but we're going to subtract 2x. So the width is actually 10 minus 2x. And the length is 10 minus 2x, and the height will be x. So the volume of my box is 10 minus 2x quantity squared times x. I'm going to go ahead and just take the derivative of that using the product rule rather than multiplying that square out and see what I get. So I have the first times the derivative of the second plus the second times the derivative of the first. I can factor out a 10 minus 2x from both of these terms. So then I'm left with one of these 10 minus 2x, and this mess becomes 2 times negative 2 times x, so negative 4x. So I end up with 10 minus 2x times 10 minus 6x equals 0. That means that either 10 minus 2x equals 0 or 10 minus 6x equals 0. Simplifying, that means x equals 5 or x equals 5/3. I have two answers. Which one's right? Well, if my x was 5, then that means I pretty much just cut the box into 4 pieces. If I have x equals 5, my volume will be 0. So that is not the right answer. That gives me the minimum box. This is the right answer over here. So, to recap, when we do max-min problems, read the whole thing. Think about what's important, what's not important. Don't get bogged down by looking at the whole thing at once. Break down the smaller details. Sketch a picture. Put variables where there need to be variables. Come up with your equation. If you don't know how to find the area of a square, then I'm very sad for you. If you don't know the area of a weird hexagon or something, Google is your friend. Look it up. Or ask me. Google is better. So come up with the equation. And once you come up with the equation in one variable, you take the derivative, set equal to 0, and solve. That's your mantra. Take the derivative, set equal to 0, and solve. That will give you the maximum or the minimum of your equation. And the best thing to do to get better at this is to practice as many problems as you can. So I wish you luck, and I will see you in class.